Light has no point of origin in any ordinary sense of the word. Sit with that statement for a moment and let it settle, because this single compact claim carries the power to dismantle almost every assumption you have ever held about the nature of the cosmos. I am not saying this for dramatic effect, and I am not trying to manufacture wonder through carefully polished language. I am saying it because it is a direct, unavoidable, mathematically airtight, and empirically confirmed consequence of the most rigorously tested, repeatedly verified, and unquestionably successful theoretical framework in the history of human thought, the theory of special relativity. That theory has been subjected to relentless examination under an enormous range of conditions, and it has emerged intact from every challenge. Its predictions confirmed to extraordinary precision. And what is the central message it delivers? It tells us, with absolute clarity and without any ambiguity, that from the intrinsic standpoint of light itself, the passage of time is entirely absent, not a tiny fraction of a second, not an infinitely small sliver of duration, but exactly, definitively, and permanently zero. Let us truly consider what that means. It means a photon of light did not spend 13.8 billion years crossing the vast expanses of the cosmos before finally reaching your eye from its own inherent frame of reference. It left its source and arrived at your retina in the very same instantaneous moment. There was no journey, no interval of transit, no ticking of any clock, and therefore no beginning to its existence at all. So when cosmologists tell us the universe is 13.8 billion years old, they are describing a timescale to which light, in its fundamental nature, is completely indifferent. And when you ask, what is the age of light? You are posing a question that physics itself declares to be unanswerable in principle. Light does not merely lack a starting point. It does not experience the flow of time at all, and it never has. Why, then, do we continue to assume that it must have one? I know exactly what is running through your mind right now. You are probably thinking this is just a clever semantic game, an elaborate manipulation of coordinate systems designed to sound profound. You are telling yourself, fine, that may be true from light's perspective, but we are not light. We live in a different frame of reference, and that is the one that matters for everyday experience. And you would be entirely correct. Yet here is a crucial point that must be grasped. That response, while factually accurate, fails to recognize something of enormous importance, something most science communicators are either reluctant to state openly or have not fully thought through. If we use time as a measuring stick for the age of the universe, and light exists entirely outside that temporal structure, then light is not bound by the universe's age in any way, shape, or form. This is not a philosophical curiosity. It creates a real, tangible problem. An issue that confronts not only philosophers in armchairs, but physicists dealing with observational data that stubbornly refuses to match the predictions of the standard cosmological model. It is a challenge facing us directly, and it deserves our full attention. Before we go any deeper into this intellectual terrain, I want to be completely clear about the operating philosophy of this channel. I am not going to quote a famous physicist and ask you to accept their statements as unquestionable truth. I am not going to tell you what the definitive interpretation of the data must be. Instead, I will methodically walk you through the actual experimental results, the solid mathematical structures that support them, and the empirically verified physical consequences that follow. After that, I will leave the drawing conclusions to you, because that is what intellectually honest scientific practice requires. It is not about deferring to authority. It is about following the method and seeing where it leads. And if at any point during this exploration you feel frustration, I urge you to lean into that feeling and hold on to it. Frustration is a natural response that arises when your existing mental framework collides with something objectively real that it cannot accommodate. That sensation is not confusion. It is your brain detecting an inconsistency that your formal education never gave you the conceptual tools to resolve. Most people instinctively pull back from that discomfort, but you chose to click on this video, which suggests you are made of different material. So let us not retreat. Let us move deeper into the heart of the matter. There are 4 fundamental concepts you must grasp thoroughly before the central thesis of this video can land with its full intellectual force. And I will be completely honest with you. I am deliberately making this exposition rigorous. I am not doing it to show off knowledge or to artificially lengthen the presentation. I am doing it because without these 4 pillars firmly in place, What follows will likely seem like abstract philosophy, and it is not philosophy. It is physics, the most foundational physics we possess. So stay with me. Let us build this conceptual structure carefully from the ground up. The first element you need to understand firmly is the real meaning of a reference frame in physics. I am not talking about the casual version you might hear in everyday conversation. I am talking about the rigorous physical definition. A reference frame is, at its core, a coordinate system relative to which all measurements are made. When you sit still and watch a car pass you at 60 miles per hour, that is the speed of the car is measured in your particular reference frame. From the driver's frame, however, you are the one moving at 60 miles per hour in the opposite direction. Here's the critical insight. Both of those measurements are equally valid. Neither is more fundamentally true or real than the other. This is not a statement of philosophical relativism. It is an established physical fact confirmed by a host of testable consequences. This is where the situation becomes extremely serious. In 1905, Albert Einstein showed that the laws of physics, including the inviolable and constant speed of light, are the same in every inertial reference frame. That may sound like a reasonable and straightforward idea, but the logical conclusions that follow from it are nothing short of mind-altering. If light always travels at the same speed, no matter which frame you measure from, then time itself must be the quantity that changes between those frames. The universe adjusts time in order to keep the speed of light constant. The universe does not care about protecting your personal sense of time. Its only concern is the speed of light. You are the variable. Light is the fixed constant. And once you truly internalize this radical inversion of perspective, physics stops being a collection of separate facts and becomes a single, coherent, and deeply unsettling argument. The second pillar we must establish is the concept of time dilation. I ask you to set aside every analogy you have ever been given about this phenomenon, because most of them are inaccurate in precisely the ways that matter most for our discussion. Time dilation is not an illusion. It is not a trick of perception. It is physically and demonstrably real. We know this with certainty because we have measured it. When highly precise atomic clocks are flown on commercial airliners at ordinary cruising speeds and then returned to ground, they are found to be measurably out of sync with identical clocks that stayed on Earth's surface. The difference is extremely small at those speeds, but it is real, and it matches the equations of special relativity with exceptional accuracy. The GPS satellites that make your phone's navigation system work experience time dilation, so significant that if engineers did not actively correct for it, your location would drift by several kilometers every day. This is not a theoretical abstraction. It is a concrete engineering requirement for modern technology. Time dilation is as real and tangible as gravity itself. Here is what the fundamental equation shows when velocity approaches the speed of light. The time experienced by a moving object, what physicists call proper time, becomes smaller and smaller. As the speed of an object approaches c, the speed of light, its proper time asymptotically approaches zero. And at exactly c, proper time equals zero. For a massless particle such as a photon, which the laws of physics require to travel at precisely c, no proper time elapses between any two events along its path, ever. The photon that left a star 10 billion light-years away and has just struck the mirror of your telescope did not undergo a 10 billion-year journey. It underwent no journey at all. From its frame of reference, emission and detection were simultaneous events. The journey you measured lasted 10 billion years. The photon measured nothing. Same event, same photon, two completely irreconcilable durations, and both are physically correct. This is not a paradox. It is a fundamental feature of our universe. The third foundational concept is the space-time interval. This is the crucial bridge that connects what we have just discussed to the larger argument we are building. In special relativity, there exists a quantity known as a space-time interval, often written as ds superscript 2. This quantity unifies space and time into a single geometric measure. For ordinary massive objects moving through space-time, this interval is positive and finite. For light, for photons, the space-time interval is exactly zero. Physicists call this a null geodesic, a path through space-time that has zero length. Consider the profound implications of that fact. Between any 2 points on a photon's world line, the space-time distance is effectively zero. The photon's origin and its destination, no matter how unimaginably far apart they appear in our reference frame, are geometrically adjacent in the four-dimensional geometry of spacetime. The photon does not travel across the universe in any precise geometric sense. It does not travel at all. It simply connects two points that spacetime itself regards as collocated. I urge you to pause and reflect on that realization, because this is where most discussions of the topic stop. They present the mind-bending fact, and then quickly move on. But the implication of a null geodesic is not merely that light has no proper time. It is that light has no space-time extent whatsoever. It exists, in the most literal geometric sense, outside what we call the universe's temporal timeline. It belongs to an entirely different category of reality. The fourth and final foundation is the cosmological timeline itself. According to the standard model of cosmology, known as lambda CDM, the universe began in an extremely hot, dense state approximately 13.8 billion years ago. In its earliest epochs, the universe was an opaque fog of plasma. Photons were constantly scattering off free electrons and could not travel freely through space. Then, roughly 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. The universe became transparent, and the photons were finally free. That monumental release is what we observe today as the cosmic microwave background radiation, or CMB. These ancient photons have been traveling for about 13.4 billion years, and we now detect them as a faint, nearly uniform glow of microwave radiation coming from every direction in the sky. This is where the central question of this video becomes unavoidable. We confidently say those CMB photons are 13.4 billion years old. Yet from a photon's own frame of reference, they are 0 seconds old. They were emitted and detected in the same instantaneous moment. So when we say the universe is 13.8 billion years old, we are describing a duration that is real and deeply meaningful for every particle that is mass, for every clock, for every observer who experiences the unfolding of time. But light, the primary means by which we observe the universe, the very medium through which nearly all our cosmological data reaches us, exists entirely outside that description. We are using an ageless messenger to reconstruct the history of a universe defined by its age. And no one in your education ever stopped to ask whether this creates a fundamental measurement problem. Now I want you to make a prediction. Before I reveal where this line of reasoning ultimately leads, I want you to commit to a position based on what you now understand about null geodesics, proper time, and the cosmic microwave background. Form a prediction in your own mind. If light truly has no temporal extent, no age, and no duration of existence, does the phrase the age of the universe have a physically rigorous meaning when applied to light itself? Think carefully. Do not simply react. Actually reason through it. Because most people, when they first encounter this idea, tend to move in one of two directions, and both miss something critically important. Some will say, yes, of course age applies to the universe as a whole, not to individual photons, and those CMB photons are 13.4 billion years old in the only frame that truly matters, ours. Others will argue no, age is a frame-dependent quantity, and is therefore meaningless when applied to anything traveling at the speed of light. Commit to one of those positions before we continue, because in a few minutes both of those answers are going to look incomplete in ways that have enormous consequences for how we fundamentally understand cosmology. We are going to test your assumptions against the cold, unyielding reality of the empirical data. Here is what the data actually shows us. The WMAP satellite and, more recently, the Planck satellite have given us the most detailed maps of the cosmic microwave background ever produced. What they found was astonishing in its precision. The CMB is almost perfectly uniform across the entire sky. The temperature variation from one point to another is less than 1 part in 100,000. And this remarkable uniformity gives rise to a major puzzle known as the horizon problem. The regions of the early universe that emitted the CMB photons we now receive from opposite sides of the sky were, at the time of emission, separated by distances so vast that they could never have been in causal contact. There simply was not enough time, even allowing for travel at the speed of light, for any information to pass between them and equalize their temperatures. Yet we observe that they have exactly the same temperature. The standard answer to this puzzle is the theory of inflation, which postulates a period of exponential, superluminal expansion in the universe's first infinitesimal fraction of a second. That expansion would have stretched a tiny causally connected region to the size of the entire observable universe. Inflation is a compelling and elegant theoretical construct. It elegantly explains the uniformity of a CMB and the observed flatness of the universe. It even makes predictions that later observations have confirmed. But here is what is rarely stated in the same breath. Inflation remains a hypothesis, a highly well-supported hypothesis, yes, but not an established certainty. And here's the point directly relevant to our argument. The horizon problem exists only because we are making a fundamental assumption. We are assuming that causal connection requires time. We are assuming that signals need duration to travel across space. We are assuming that the universe's history is strictly a temporal sequence. All of these assumptions work perfectly for massive particles. But photons are not massive particles. And the horizon problem looks very different if you take seriously the fact that, from a photon's null geodesic, the entire observable universe is in a sense geometrically interconnected. I am not claiming that this solves the horizon problem. What I am claiming is that almost no one is asking this question with sufficient force, and it is a question that clearly deserves our full attention. Now, let us turn to what happened in 2022 and 2023, because the James Webb Space Telescope fundamentally changed the conversation in ways that are still sending shockwaves through the physics community. JWST was specifically designed to look further back in time than any previous telescope. Its first deep-field images were breathtakingly beautiful, but what they revealed was also scientifically unsettling. Webb detected fully formed, massive galaxies at redshifts corresponding to a time less than 700 million years after Big Bang. These were galaxies that, according to our standard models of structure formation, should not have had enough time to assemble into such large-scale structures. The standard model of cosmology says that after the release of the CMB, matter needed hundreds of millions of years to slowly gather under gravity. Small structures formed first, then larger ones merged and grew. This is called hierarchical structure formation. Webb's early galaxies simply do not fit that timeline. They are too large, too well organized, and too chemically evolved to have formed in the time the model allows. And the physics community's reaction has been exactly what honest scientific practice should look like. It was not denial and it was not silence. It was genuine, tangible uncertainty. New models are being proposed rapidly. Modifications to behavior of dark matter, alternative inflation scenarios, the introduction of early dark energy. None of them has definitively resolved the tension. And underlying all those proposed solutions is the same foundational assumption that we can use light to measure time, and that the duration light has been traveling is a straightforward proxy for the age of the structures it reveals. Webb found galaxies that should not yet exist. And every proposed solution assumes that light's travel time is equivalent to the universe's developmental time. But what if that assumption is precisely where the problem lies? What if the issue is not with the galaxies themselves, but with the measuring stick we are using? This is where I am going to ask you to do something genuinely difficult. I want you to hold three competing interpretations of everything we have established so far in your mind at the same time, without forcing them into one neat final answer. This is the point at which most science communication fails you. It chooses a tedious interpretation, presents it as a consensus, and moves on. This channel refuses to do that. So here are the three frameworks that physicists and philosophers of physics actually debate when they work through the deep implications of null geodesics and cosmic time. The first interpretation is the relational time view. This position holds that time is not a background feature of the universe that exists independently of the things inside it. Instead, time is a relationship between physical systems. Specifically, time is defined as what clocks measure, and a clock is any physical system that undergoes a change of state. Light, however, does not undergo internal state changes as it travels through space. It has no internal clock. Therefore, asking about light's experience of time is not a deep question about the nature of reality. It is a category error. The question, how old is light, is like asking what is north of the North Pole. The framework that generates the question simply does not apply to the subject. Proponents of this view, who often draw on the work of physicist Julian Barber and his explorations of timeless physics, would argue that the age of the universe is defined by the progression of massive clocks, and light is simply not one of them. The problem with this interpretation, however, is that it fails to explain why light's null geodesic has real, tangible geometric consequences for how we measure the structure of space-time. It addresses the temporal question, but sidesteps the geometric one, and that sidestep is not a minor oversight. It is precisely where the real tension in physics lies. The second interpretation is the structural realism view. This position contends that what is fundamentally real are not the individual objects of physics, but the relationships and the underlying structures that the mathematics describes. According to this perspective, light's null geodesic is not a limitation or an anomaly to be explained away. It is telling us something profoundly true about the inherent structure of space-time itself. Specifically, it is indicating that the universe does not possess a single, unified temporal structure in which all physical entities participate equally. Massless fields occupy a fundamentally different geometric role than massive particles. They do not evolve through time. Rather, they connect points across space-time. And the universe's history, as we reconstruct it from light, is therefore not a direct readout of what happened in a temporal sense. It is a projection of a geometric structure onto a temporal framework that applies only to part of what exists. The implication of this view is significant and far-reaching. Our cosmological timeline is real and meaningful for the matter content of the universe, but it may systematically misrepresent the behavior of the fields, particularly the electromagnetic fields, that we use to observe that matter. We are reconstructing the history of the cosmos with a messenger that retains no memory of the journey it took. This could account, at least in part, for why Webb's observations continue to surprise us. We are reading a temporal map drawn by something that has never inhabited time. The third interpretation is the modified cosmology view, and this is where matters become most technically contested, but also most consequential. A growing number of physicists, including those publishing in peer-reviewed journals as recently as 2024, have begun investigating whether the concept of universal age is operationally well-defined at all, not philosophically, but operationally. Meaning, is there a physical procedure one could carry out that would yield an unambiguous answer for the age of the universe that does not depend on which type of physical system you use as your clock? For massive particles and atomic clocks, the answer is yes. For photons, it is demonstrably no. Some researchers working in this area, particularly those involved in quantum gravity approaches such as loop quantum gravity and causal set theory, propose that time itself is an emergent property, not a fundamental one. At the deepest, most fundamental level of physical description, time does not exist. What we call time is what appears when the underlying quantum gravitational degrees of freedom coarse-grain into the smooth space-time we experience in everyday life. And if time is emergent, then the question of what light experiences is not a question about a special case. It is a window into the pre-emergent, timeless structure of reality itself. This interpretation is the least settled, but it is also the one most consistent with the very frontier of theoretical physics in 2024 and 2025. Its strength is that it naturally accommodates both the null geodesic result and the anomalies in large-scale structure formation that Webb has revealed. Its weakness is that it is radically incomplete. We do not have a working theory of quantum gravity. We have approaches, frameworks, and candidates, but none has been empirically confirmed. So this interpretation is honest about what we do not know in ways the other two are not. But it also offers the least traction for generating specific, testable predictions at the present moment. You probably disagree with at least one of these three frameworks. Excellent. I want to disagree with one of them. Not because disagreement is a goal in itself, but because the moment you feel resistance to one of them, you are actively doing physics. You are actively asking, what would have to be true for this interpretation to be correct? And more importantly, is that something I am willing to accept on the basis of the available evidence? That is not a rhetorical question. That is the actual intellectual work. Three frameworks, three completely distinct answers to what light's timelessness implies for cosmology. All three are supported by legitimate physics. None is definitively proven. That is not a failure of science. That is what the frontier of human knowledge actually looks like. And most YouTube channels simply will not show you that unsettling truth. Now I want to share where I personally stand on this issue, and I want to be exceptionally precise about what I am doing when I state it. This is not a final conclusion. It is not a declaration of what the science unequivocally says. It is simply one interpretation of what the science makes available, and I am revealing my reading of it so that you can challenge it, refine it, or reject it entirely. That is the only honest way to engage with this material. The null geodesic result does not strike me as a category error. It strikes me as a signal. When a physical framework returns 0 for a measurement, that is typically not a sign that the question is malformed. It is usually a sign that 0 is the actual answer, and that this answer carries deep implications we have not fully pursued. What I believe the null geodesic is telling us is that the universe contains two genuinely distinct kinds of physical existence. One that fully participates in time, the matter sector, which includes massive particles, atoms, galaxies, you and me, and one that connects points in time without residing within it, the radiation sector, which includes photons and the electromagnetic field. And the fact that we construct our entire cosmological picture, our timeline, our distance measurements, our age estimates, and our structure formation models, almost entirely from the second category, while assuming it behaves exactly like the first, appears to me as a foundational assumption that deserves significantly more scrutiny than it currently receives. Research coming from groups working on causal set theory, particularly work published in Physical Review Letters in 2024 that examine discrete spacetime structure and photon propagation, suggests that the concept of photons' age is not merely an interesting philosophical puzzle, but a genuine physical question with testable consequences for how we interpret cosmological data. These investigations indicate that if spacetime is fundamentally discrete at the Planck scale, then the null geodesic of a photon might not be exactly 0, but could acquire a tiny non-zero effective duration due to the granularity of spacetime itself. This is a prediction that could, in principle, be tested with future observations of high-energy gamma rays from distant astrophysical sources. If such a deviation from 0 proper time were detected, it would fundamentally alter our understanding of both light and the nature of time itself. It would mean that light does have a beginning or at least a measurable duration, but one so minuscule that it is effectively 0 for all practical purposes, yet non-zero in a way that reveals the underlying quantum structure of space-time. This is a kind of frontier physics that is happening right now, and it is directly relevant to the questions we have been exploring. Furthermore, the data from JWST continues to accumulate, and each new dataset adds another layer of complexity to the picture. The galaxies that Webb has found are not just massive, they are also surprisingly chemically enriched. They contain elements such as oxygen and carbon that, according to standard stellar nucleosynthesis timelines, should have required several generations of stars to produce. This chemical maturity, combined with their structural maturity, presents a double challenge to the standard timeline. It is as if we are finding fully grown trees in a garden we believe was only seeded a few years ago. Something is systematically wrong with our chronological assumptions, and the null geodesic of light is a prime candidate for where the flaw might reside. If light does not experience time, then the distances we infer from its travel time might not correspond to the developmental time of the structures we observe. We might be looking at a universe that is geometrically interconnected in ways our temporal framework cannot capture. And this interconnectedness might allow for the rapid formation of structures that appear impossibly old from our temporal perspective. Let us also consider the implications for the cosmic microwave background itself. The CMB is often described as the afterglow of the Big Bang, a snapshot of the universe at the moment it became transparent. From our perspective, that snapshot is 13.4 billion years old. From the photon's perspective, it is simultaneous with their detection. We are therefore using an instantaneous geometric connection to reconstruct a temporal history. That is not a minor technical detail. It is a foundational feature of how cosmological knowledge is obtained. And until we confront the possibility that the messenger we rely on does not share the temporal structure we're trying to measure, we will continue to encounter anomalies that look like problems with the galaxies or the models when the deeper issue may lie in the very yardstick we're using. This is not the end of the discussion. It is the beginning of a more rigorous one. The null geodesic is not a curiosity to be noted and then set aside. It is a structural feature of space-time that forces us to ask whether the age of the universe, as we currently define it, is as universal as we have assumed. Light does not possess a point of origin in any conventional sense. That fact is not philosophy. It is physics, and the consequences of taking it seriously are still unfolding.